So now that we know in a bit more detail what independence and randomness are, let us turn to fairness. Now, fairness is just a combination of randomness and independence. So a process is fair just in case, first, it is random, second, the outcomes are always independent. So this just corresponds to, on the roulette wheel from the beginning, that first, every spin of the roulette wheel will land randomly on one of the 38 segments. And secondly, no matter what has happened on earlier spins, that doesn't affect how later spins will turn out. Now, just like the word bias has a certain moral or kind of ethical connotation, similarly in ordinary language, the word fair does as well. So it's good to be fair, and it's bad to be unfair. But I want to note that I do not mean fair in this ordinary moral sense. Um, Here it's just a technical term that's used and has nothing to do with what's good or bad or right and wrong. It simply has to do with a certain process, whether the process is random, whether each outcome for each part of the process is random, and whether the outcomes are independent. That's simply what I mean by a process being fair. So as some exercises, let's think about whether certain processes are fair or not. So suppose you toss an ordinary coin a whole bunch of times. Is this fair or unfair? It is fair. So on each toss, heads and tails are equally likely because it's an ordinary coin. So that means that it's random between heads and tails, or another way of putting it is that it's not biased, just unbiased. There is no bias between heads or tails. And furthermore, the outcome of one toss doesn't affect the probability of the next toss because each toss is independent. Each time you toss it, it's a new toss. So every time is 50-50 between heads and tails. So the process of flipping an ordinary coin a whole bunch of times is fair. Now suppose you draw with replacement from an urn containing black and white marbles, and the urn we had from before had 50 black marbles and 50 white marbles. So suppose you draw with replacement from this urn with half black marbles and half white marbles, and you draw a whole bunch of times, replacing after each draw what you drew on the previous draw. Is this process fair or unfair? The answer is that this process is fair. On each draw, black and white are equally likely. That is, on each draw, it's random between black and white. And the outcome of one draw doesn't affect the probabilities of the other ones because you're putting the ball back in. So that is to say that the outcomes of this process are independent. So each time you draw, there's 50 black marbles and there's 50 white marbles. And so each time you draw, there's a half chance of drawing black and a half chance of drawing white. So here are two examples of fair processes. So now that we have in a bit more detail the concept of fairness, which has two constituents, it has randomness and independence as its parts, let us return to the gambler's fallacy, which we began with. So gambling usually involves fair processes. It involves fair dice, fair roulette wheels, fair decks of cards. So you assume when you go, for instance, if you were to go to a casino, that the casino is not going to be playing any tricks with you with the dice or the roulette wheels, etc. But the thing is, sometimes people forget that in a fair process, there's independence. So again, independence is one of the two parts of what it means for a process to be fair. And what leads to the gambler's fallacy is that people forget that independence is a part of fairness. So if the roulette wheel comes up black 5 times in a row, they figure it's due for a red. Or if they get a bunch of bad hands in a row, they figure they're due for a good one. And the gambler's fallacy is reasoning about a fair process as if the outcomes were not independent, i.e., as if the outcomes were dependent, when in fact you know that they're actually independent. So thinking because you have a fair, normal roulette wheel that's come up black 5, 9, 12 times in a row, to think because it's fair, because it's totally random and independent, to think that for some reason it's actually not independent. And that is the gambler's fallacy. But the gambler's fallacy is not so simple. That is to say that there are some cases in which we can infer that a process is dependent, and it is not fallacious for us to do so. So imagine you find a coin on the ground and you flip it 100 times. So you're just walking along and you just randomly and you find a coin lying on the ground and you decide to start flipping it. And you have no idea about where this coin came from or anything like that. Now you flip it 100 times and this coin lands heads every time. In this case, shouldn't you conclude that the next toss will almost certainly be heads? So if this coin you found on the ground, which you have no idea how it was made or where it came from, if it lands heads every time 100 times, isn't the right thing to conclude that it's actually going to keep on landing heads, that there's something fishy about this coin? But given that it seems reasonable to conclude that, does that thereby mean that the gambler's fallacy isn't a real fallacy? That is to say that this gambler's fallacy, we're committing it, but it's actually not bad to commit it. Well, yes and no. So yes to the first part, which is that you should conclude that the next toss will almost certainly be heads. So if you have no idea about how this coin works or where it came from, and if it comes up heads every time over and over and over, then yes, the right thing to do is to conclude that it's going to keep on landing heads. But that does not mean that the gambler's fallacy isn't a thing. Because the reason you should conclude that the coin is going to keep on landing heads is precisely because you conclude that the coin isn't fair. And the gambler's fallacy is only holds when there's a process which you know is fair and you reason on that basis that you're, for instance, due for black or due for a red. But that reasoning in thinking that because a process is fair, that you'll be due for a certain outcome, that is a gambler's fallacy. So again, if you know a process is fair, yet you reason as if it were not, that's what the gambler's fallacy is. But if you don't know whether a process is fair, and then you learn that it probably isn't. So for instance, you find a coin, and then by flipping it, you learn that this coin is probably a biased coin. That's not a fallacy. In that case, in the case where you conclude that the coin is not fair, you're simply using evidence to determine whether it's fair or not. And that is different than the gambler's fallacy, who thinks, oh, this roulette wheel is totally normal. There's nothing suspicious happening. Therefore, since the roulette wheel has landed, let's say, red 12 times in a row, because it's a totally normal wheel, and that's a very unlikely outcome of it landing red 12 times in a row, I'm therefore due for a black. And that reasoning that we looked at the very beginning is the gambler's fallacy, because you're concluding from the thought that a process is fair that is not fair, and that is a fallacy. But in the case where you find a coin on the ground and you have no idea its constitution or its origin, and you realize that when you flip it, it always comes up heads, in that case, what's at issue is precisely whether that coin is fair, and you are able to conclude from the evidence that the coin is not fair. So to conclude, as I mentioned at the beginning of this lecture, next week we will start developing formal tools of probability theory that will help us understand some of these probabilistic notions, which we have introduced this week.